Good morning, everybody. Sorry for that little delay. My name is Jacob Kazmi. I'm part of Dr. Becker's team. I'm one of the PhD students in the lab. And I was asked to talk a little bit today about considerations of the immune system as we move forward with systemic mitochondrial therapies. And as Dr. Walker pointed out earlier today, as we move more into human trials, I think the immune system can be a key challenge, but also perhaps opportunity. So we can think about this relationship kind of moving in two directions. On one hand, we know that mitochondria are inherently linked to the function of most immune cells and can influence their function. And then on the other hand, we know that immune cells might target mitochondria or alter somehow how extracellular mitochondria may be working. So I want to talk about both of these. First, how can mitochondrial transplantation alter immune function? And this work comes from this concept of immunometabolism. Which is that metabolic states of immune cells are tied to their function. And we can go through a variety of different cell types as an example, but I've chosen the monocytes where this has been really well characterized. And for those who maybe aren't as familiar, monocytes can be divided into a number of subsets, but for simplicity's sake, we just focus on two. The classical monocytes over on your right side, which are tissue-infiltrating monocytes, what we think about classically as cells turning into macrophages during inflammation, versus non-classical monocytes, or patrolling monocytes that stay within the vasculature and clean up debris and look for inflammatory signals. Interestingly, looking at the metabolism of these two subsets of monocytes, we see that they have some stark differences. Classical monocytes are more glycolytic in nature, where non-classical monocytes are more respiratory. And this is tied again to their function. You think about classical monocyte going deep into tissue, away from capillary beds, where it may not have access to oxygen-rich blood. This will allow it to be more robust and survive. On the other hand, we also know that biochemical intermediates can trigger cytokine production. This work comes from macrophages and are closely tied to cytokine production in phagocytic cells generally. And again, we could go through a number of examples, but just focusing on the citrate as one biochemical intermediate. Through a series of interactions, we know it can be converted into other intermediates. In this case, we can look at acetyl-CoA and itaconate particularly. And downstream, through different protein messengers, this can lead to the production of IL-10, canonical anti-inflammatory cytokine, versus things like IL-1 beta or IL-6, pro-inflammatory cytokines. And you might be asking, well, how can this both be true at the same time? And the key is metabolic switches, which is something that we're actively looking into. I just want to share a little bit of the data from our lab. The Becker lab focuses on cardiac arrest mainly. And we use a couple of different models. So this work was done by Kei Hayashida in the lab and published a few years ago. And he used a rat model of asphyxial cardiac arrest. So these rats receive a period of about 10 minutes of arrest time, after which we initiate CPR and provide adrenaline, as well as either intravenous mitochondria or vehicle. And we use a couple of different mitochondrial preparations in this work. We have freshly isolated skeletal mitochondria, which you can see up in that red line, as compared to mitochondria that have gone through a number of freeze-thaw cycles, thus greatly hindering its function. And I hope you can appreciate that the freshly isolated mitochondria increase survival to about 95%, whereas the frozen thawed mitochondria or vehicle remain around 55%. And this raises the question of, again, as Dr. McCauley mentioned this morning, how functionality might be driving the benefits that we see in vivo. Since these were systemically administered, as I said, intravenously, we wondered how the immune cells might be interacting with these mitochondria. And we moved to the mouse, where we have a much better understanding of different markers of immune cells that allow us to analyze them by flow cytometry. And we used, again, skeletal muscle mitochondria. Here we labeled them exogenously using the A fluorescent dye, and introduced them again intravenously into recipient mice. Looking at a variety of immune cells through flow cytometry, again, I'm just going to focus on monocytes here, rather than going through each one specifically. But we see a large uptake both in sham animals that did not receive cardiac arrest, as well as the cardiac arrest animals. And what I really want to point out here is the difference in uptake that we see between these two animals, which suggests to us that somehow state might be modulating these immune interactions as well. When we look at the organs, again, just a few of them, the brain, heart, and spleen, this is at about 1 hour post the transplantation, we see an increase in fluorescent signal. This is through an in vivo imaging system. You can see an increase in fluorescent signal in the mitochondria-treated groups. But interestingly, we did not see this at very early time points, which suggests perhaps a delayed redistribution. And we have a couple of models that we've been thinking about in how this immune function might be altered and maybe providing functional benefits in our rats. One is what we're calling an altered effector function model, which is that mitochondria interact with immune cells and perhaps are taken up in the vasculature. And when those immune cells reach target organs, they have an altered phenotype. The other is a subsequent transfer or delayed reuptake and redistribution model, in which in the vasculature, again, mitochondria might be taken up, and then once those immune cells reach dead organs, either perform a subsequent transfer of those same mitochondria or are encouraged to transfer their own endogenous mitochondrial pools. And I know in the next session we have a presentation on that. Really interesting. And finally, I just want to end talking about mitochondrial damps or damage-associated molecular patterns and considerations for mitochondrial therapies. So for those who don't know, damps are kind of a collective term used to refer to molecules that might trigger immunity. And mitochondria are full of them. And we know a lot of this from autoimmune work, where patients might have circulating anti-mitochondrial antibodies. And as we think about transplanting more mitochondria into humans, we might start to see this come into play. So at first sight, this might be a cause for concern, perhaps might decrease the efficacy or function of our mitochondrial therapies. But we've been thinking about this in the lab as perhaps an opportunity. Maybe these damps are facilitating interaction with immune cells and thus leading to the functional benefits that we see. And with that, I just want to thank everybody in the lab. I'm going to go through them all here, but thank you, everybody.
All right, keeping us honest and back on time, despite the little rough start from our side. We come to one question.
Hi, thanks. Thank you. We think a lot about these things in our lab as well. And so naked mitochondria should have displayed many sort of NDAMs on their outer membrane, right? So a lot of times I ask, are these naked mitochondria or are they mitovesicles, so enveloped in plasma membrane that have, receptors that kind of could potentially direct a whole host of interactions on the cell surface, signaling within cells, right? So I think my question is, naked mitochondria versus mitovesicles, as we like to call them, could potentially have really different effects on the immune system. And I just was hoping we could have that conversation, and you seem like the good person to initiate that. And we've found a lot of very different effects based on how we isolate our mitochondria, how we handle them, what their cargoes, what the EV cargoes look like, what is the functionality of the mitochondria within them. So sorry for the rambling question, but I was just hoping you might address that.
Absolutely, that's something we've been thinking about a lot too. I know that on the EV side, there also comes a double-edged sword with the concern of maybe MHC class 1 or perhaps MHC class 2, depending on what your cell of origin is for these EVs. So I don't think that one or the other is necessarily better. I think it might come down to what the disease state is. It might come down to how they're handled again as well. And the niche, exactly. Thank you so much.
I'm totally open for time for one more question.
This is a brief comment. I don't know if there are any cancer biologists in the audience, but I just came from the AAP meetings in Chicago, which were fantastic. And there was a talk from UT Southwestern on the fact that metastatic cells actually have a lot of mitochondrial activity. And they're not engaging in the Warburg effect, which we all learned is what's going on in a tumor. that somehow the metastatic cells undergo a switch to the TCA cycle. And maybe since there are different types of mitochondria, maybe that's not the key thing. It's just a different kind of mitochondria. But anyway, just want to bring it up.
That's a great point, and I think, looking at the work of someone like Craig Thompson at MSK, who, kind of fitting with Dr. Picard's mitotypes, has also kind of pointed that out in the cancer space.